Previously, we've discussed how to solve proportions when we have a ratio set equal to another ratio. Now we're going to use these proportions to find missing side lengths in similar figures. We can also bring in some real-world distance problems to help us solve in some application problems. Similar figures have the same shape but not necessarily the same size. So this is like taking a shape, putting it into a copy machine, and blowing it up. So a couple different vocabulary to go through with similar figures. The little wavy line means similar to. So when I see this next symbol here, this is stating that triangle ABC is similar to triangle FGH. So it is the same shape, but not necessarily the same size. It's like I took that triangle ABC and I blew it up. So everything grows and it grows at the same rate. With that similarity statement that I've boxed in, those also tell us all the corresponding sides in the triangle. So if you notice in that similarity statement, A and B are the first two letters and F and G are the first two letters. So that means that side AB corresponds with side FG, meaning that they're in the same place of that triangle, so they are corresponding with each other. If I look at another pair of letters in that similarity statement, B and C are the last two, and so are G and H. So side BC is going to correspond with side GH. And then lastly, if I look at the first and the last letters of the similarity statement, C and A are the first and last, and H and F are the first and last. So side CA corresponds with side HF. The reason why this is helpful is because now this helps me set up my proportions when I'm solving for a missing side. So when I set up my proportions, these are always going to be set up in the same order. So notice how in the first ratio, it was AB over FG. So we took a side from the triangle on the left and put it over a triangle from the right side of the picture. And you'll notice that each one of those other ratios in the proportion follows that same pattern. We always did left over right. It's important when you're setting up your proportions to set them up in the same corresponding order. Also, in similar figures, all angles are congruent. Congruent means that they have the same measure. So if angle A is 40 degrees, angle F is going to be 40 degrees because they're corresponding. So when I look at this example, it says triangle ABC is congruent to triangle DEF. So when I look at my similarity statement, I can see that AB corresponds to side DE. They're in the same corresponding spot. I can also see in my similarity statement that side BC corresponds with side EF. So BC and side EF. Well, it is telling me we'll find out what is DE. So when I set up my proportion, I always start with two corresponding sides where I know the measures in both triangles. Well, in sides BC and EF, they're corresponding, and I know the measurements of both. I know that BC is 16 and EF is 12. So I'm going to set up a ratio of 16 over 12. Notice I did left over right. So when I set up my other proportion, I need to do left over right. My second ratio is going to include the missing side that I'm trying to find, which is DE. It corresponds to side AB. AB is coming from the left triangle, so its measure is going to go on the top of my ratio. So I have 10 over, I'm going to put X because I don't know what side DE is. That's what I'm trying to find. Then just like we talked previously, to solve a proportion, we set up those cross products and solve for the missing variable. So I have the product of 16 times X is equal to the product of 12 times 10. The product of 12 times 10 is 120, and then I divide both sides by 16 to get X equals 7.5. It is realistic to have a decimal measurement in this example because it would not make sense to say that I have 120 over 16 as a measurement of that side length of DE. All right, the next example, it's asking to find side AC. So I'm wanting to find this side length here, which corresponds with this side length here. So I start with a pair of corresponding sides where I know the measurements of both. That would be side BC and side EF. I chose to do the left over the right. So when I set up my other ratio, I need to make sure I do the left over the right. My missing side is coming from the left triangle, so I'm going to have x on top, and its corresponding side is 18, which is coming from the right triangle. Setting up my cross products to solve this proportion, I will get something like 16 times 18 equals 12 times x. 16 times 18 is 288, equal to 12x. Then using inverse operations to get x by itself, I'll get an answer of x equals 24. I can also use proportions to solve some story problems that include some missing side lengths as well. When you have a person standing up next to something else and they cast shadows, when these shadows are cast, you create two similar figures of some right triangles, as you can notice in this picture. So in this example, it says the sun's rays strike the building and the girl at the same angle. So this is what is creating those two similar triangles, since they have the same angle with the sun. The two similar triangles are shown. So you notice the girl is 5 foot tall. We don't know how tall the building is. Her shadow is 3 foot in length, and the shadow of the building is 15 feet in length. So when I set up this proportion, I need to start with two corresponding sides that I know the measurements of both. I know the measurements of both shadows. So I'm going to do 15 over 3. I chose to do the building over the girl. So when I set up my other ratio, I need to do the building over the girl. So I have x, because I don't know the height of the building, over 5, the height of the girl. Now I'm setting up my cross products to solve this proportion. I have 15 times 5 equals 3 times x. When I take 15 times 5, I get 75 equal to 3x. Using inverse operations to solve out for x, I then get x equals 25 feet. Remember, it's a story problem, so you should include a label. The height of that building is 25 feet. Sometimes a picture may not be given for us within the story problem, so we have to sometimes draw a picture to help us picture those two similar figures. So it says a man who is 6 foot tall. So I'm going to draw my man here who's 6 foot tall. He's standing next to a flagpole, so here's my flagpole. The shadow of the man is 3.5 feet, so its shadow right here is 3.5, so I've created that right triangle now. And the shadow of the flagpole is 17.5 feet. Same thing, that shadow and flagpole have now created a right triangle. What is the height of the flagpole? So here's my h, my height. Remember, do things in the same order. The two corresponding sides that I know the measurements of both are the shadows, so I'm going to do 3.5 over 17.5. I chose to do boy over the flagpole, so when I set up my other ratio, I need to do the boy, so 6 over the height of the flagpole. Setting up those cross products to solve out for h, I then have 3.5h equals 17.5 times 6. Then I have 3.5h equals 105, lastly using inverse operations to get a height of 30 feet. Remember, that flagpole is 30 feet tall. Make sure you include the label. We can also use a scale on a map. Down in the bottom left-hand corner of a map, oftentimes you see a scale. That's telling you that 1 inch on the map is the same thing as 110 miles in real life. So the question is asking me, what is the actual distance from Jacksonville to Orlando? So my first ratio is just going to be my scale. I know that 1 inch is the same thing as 110 miles. So I did inches over miles. I did the distance on the map over the distance in real life. So when I set up this other ratio, I need to do the distance on the map. When I read this ruler, looks like the tick mark is stopping right about here. So that is 1 1/4 inches, or 1.25 inches. And then I'm trying to find out the distance in real life, so I'm going to keep that as x. Setting up my cross products to solve out for x. I have 1 times x equals 110 times 1.25. 1 times x is the same thing as just x, and then 110 times 1.25 is 137.5, and then I've already solved out for x since it was 1x. My label there, this was on the bottom of my proportion, so it's miles, because I'm finding the distance in real life. We can also use proportions to solve out for distances when we're using models. So if you have a model tractor or a model car, they're all proportional. They all get smaller at the same rate on every part of it. So here it says a giant model heart is shown. The heart is the ideal size for a man who is 170 feet tall. About what size would you expect the heart of a man who is 6 feet tall to be? So I'm going to start out with two measurements that I know both. Well, I know both the heights. I know the height of the man is 6 and the height of the giant is 170. So I did the actual over the giant. When I set up the other proportion, I need to do the actual over the giant. I don't know the actual distance in the heart, so it's going to be x. And the distance of the heart and the giant is 14. Setting up my cross products to solve that out, I have 170x equals 6 times 14. Continuing to solve this equation, 6 times 14 would be 84. Lastly, I'm going to divide by 170 on both sides. This answer is going to give you a long decimal in your calculator, so I'm just going to round and give an approximation, and I'm going to use my about symbols to show that it's about 498.